Thank you very much. Thank you very much, everybody, for your interest, for coming to hear about analytics with confidential data. Briefly about myself, I'm in Accenture since almost 10 years. I worked on different topics from the big data analytics, the data governance, data streaming, data security, HPC, and AI. And one of the greatest challenges that I've seen in many projects is to exploit the insight of the data without compromising the confidentiality of the data. This is not a single problem for which we are looking for a best solution. It is a complex threat surface that requires many different solutions combined together. The purpose of this talk is not to go through all these solutions, but focus on three technologies that have become mature very recently, and they have a huge potential. They're still not mainstream, but I believe in 5 years they will be mainstream. So let's start with a representative use case. I am a bank, Bank A. I want to do anti-fraud detection, anti-fraud prevention, or anti-money laundering. I have access to my customer data, account data, and also access to the transactional data with Bank B, maybe even good quality. But I certainly don't have access to the customer account data of the other banks. But this is crucial information from the point of view of predicting fraud. Was that account open very recently? For instance, this is like night and day in terms of visibility and fraud detection. What happens today? Nothing. We accept the limitations with the delight of criminals. But this does not need to be so. There is a solution today. It's called multi-party clean rooms or multi-party confidential computing. And this is, to introduce it, as an interesting history because it comes from a completely different problem. The solution comes from the, historically from the need of cloud migration. And the problems of moving in the cloud is that you have to bring to the cloud to give someone else all your precious and sensitive data. And of course, we can encrypt the data on the hard disk. The data are encrypted in communication. But still, there is the risk that the cloud administrator could potentially interfere with the data, dump the memory, and even change it. This has been mainly a theoretical risk, but it has blocked a lot of discussion about cloud migration, understandably. And for this reason, all the main chip manufacturers, they have developed their solution to this problem. The solution was not straightforward because historically the operating system and the CPU have been designed with the idea that there is one administrator that can everything. This needs to be changed. This is not a law of nature, but is something that needs to be changed at a very low level in the redesign of the architecture. And today, all major chip manufacturers are selling confidential computing solutions, and all cloud providers, they offer that with a moderate penalty on price and performance. So great. This hardware architecture include so-called trusted execution enclave that is isolated from everything else, including it is even isolated from its own operating system and the hypervisor and operating system of the host machine. Thanks to this solution, the data are always encrypted outside this trusted execution environment, and only privileged code has access to the enclave. Moreover, the solution offers cryptographic guarantees that the enclave is correctly configured, that the software is updated as expected. These capabilities are sometimes called encryption in use, that comes on top of the standard encryption at rest and encryption in transit. Now, this solution enables not only the migration to the cloud, it enables a wide range of new possibilities, including, because if I have a formal guarantees that not even the administrator can interfere with the data, and not even with the physical access to the machines, then I can offer to other parties, many parties, to bring their data in this machine and do a common processes, common analytics, with the guarantees that nobody can see the data that is not supposed to see. And this is the idea of the multi-party clean rooms. Coming back to this, the original example, what this means that both banks send their data to a central machine running a trusted execution enclave with a formal cryptographic guarantee that nobody can access the data of the other. And that the data are used only for the purpose that they are supposed to be used. And this could then generate an alert that is sent to the bank A, only with the data of the bank A, but with a score that depends on the computation done also, including the data of bank B. The use cases for this technology are countless. To mention another one, consider the problem of sharing patient data across hospitals and pharma companies and researchers. This process is highly regulated, but the regulations are often very ambiguous, and the industry is also plagued with very risky common practices. In fact, these studies here points out that 70% of the clinical trials are at risk of data breaches. And moreover, out of the top, the biggest healthcare data breaches, almost half of them happened in the last 2 years. So that's very worrying and worsening rapidly. But this is understandable because multiple entities share very sensitive data. And moreover, it is very common to adopt so-called identification methods that are not what they claim to be. But also in this case, a multi-party clean room with a trusted execution enclave would represent a great step forward, at least in some use cases. Another hugely important case is visibility on the supply chain. There are companies that invest billions to acquire other companies with the main purpose of having control on their supply chain. So wouldn't it be more cost effective to invest $1 million in a serious project to use multi-party clean rooms? It's funny that, let me then mention one last use case that I've talked about exchanging data, combining data of different parties. But we don't want to protect only data, we want to protect also software. And an extremely important use case is when there are two parties, one is data owner and another is software owner, and they want to do analytics by combining these two. And neither one wants to share his software nor the other wants to share his data. What happens today? Either nothing, it's a missed opportunity most of the time, or one of the two gives up and takes a big risk that they wouldn't like to take. But it's also not necessary, because a multi-party clean room also offers here the best solution with the guarantees and the advantages for both. Accenture has worked with multiple partners on this topic, and two very important ones are OPAC and Microsoft Azure. And encourage you to go to the talk of Giuseppe Giordano on this afternoon, that will have much deeper insight in this topic. Here I want to move. Let me go to the question. This technology is so powerful, so promising. Why is not yet everyone is using it? First, it's very recent. 1 year ago, some of these technical solutions were not there yet. And of course, there is also some legal complexity that one has to identify the right framework for all these solutions. Another complexity is the fact that it becomes more difficult to develop, for instance, to do training of, if you have a well-defined process, that's the ideal case. But if you have to train a model, identify the real processing, explore the data, that becomes more complex. And this is what I'm going to talk next. Moreover, it also requires a higher level of data quality and metadata standardization. That's also a topic that we'll discuss after. The second technology that I want to introduce is differential privacy. Consider again this case of clinical trials. In some cases, the data processing is well defined, and then that's a perfect case for multi-party clean rooms. But in other cases, we need to do some data exploration. We have to train a model. So can we enable the scientist to have insight from the data without putting the data at risk and the privacy of the patients at risk? There are some common approaches to this that have important drawbacks. One common approach to deal with these cases is simply to mask the obvious identifiers. But this does not prevent identification. It is well known that often just a couple, 2 or 3 non-sensitive attributes can identify an individual. Almost more than 80% of the US population can be identified with such attributes, for instance. Re-identification, even with high probability, it's explicitly forbidden by GDPR. Although the same regulators are often very confusing in telling what allow and what doesn't allow re-identification. So there is a huge gray zone in this. K-anonymity is also very often used. That means of grouping as I show here in the picture, instead of giving a specific age, you group the people by the ranges of age, ranges of salary, and so on. But this not only destroys very often the value of the data, it also doesn't give any clear guarantees. It has been shown that in some cases this is increasing the probability of guessing who is the individual behind the data. Well, another approach, well, I only do big aggregates. There is no risk on that. But have you considered all the possible differences of your many big aggregates? And does this protect your wealthiest customers, which are typically outliers? So, in the past decade, there has been a breakthrough in the science of data privacy protection that goes under the name of differential privacy. This is not so much in the news as much as generative AI, but the computer scientists are convinced that they have found the best solution to this problem, at least the best definition of what is the problem and what we can do and what we cannot do and what we can promise or cannot promise, stated in a precise way. This method has been initially adopted by the US Census to publish all their statistical reports since 2018, they have adopted officially. The Swiss Federal Statistical Office is exploring that. Apple, Google, Facebook, LinkedIn, Microsoft use this technology to collect reports from the users and more. Accenture has done one of the largest applications worldwide adopting this. Wikimedia uses to generate statistics about users in non-democratic countries. There are multiple white papers by academics that claim that this should be used to define precisely what GDPR means in all those aspects where GDPR is just not clear. Let me explain briefly what it is, also to demystify the idea that is a complex thing. The idea is very simple. Let me start with a simple problem. I have a data set, and if I do reports on this data set, I may run the risk of revealing some the identities of the people behind the data set. For instance, outliers are at particular risks. Now, if I remove people from the data set, certainly I'm sure that they will not violate the identity of people. In the same way, if I add noise to all the queries, all the output of all the queries, in a way that the probability of each output is almost the same whether people is there or not, then again, nobody could infer with certainty whether people was there in the first place, and nobody could even infer with a significantly increased probability whether it's there or not. And that's what is the definition of differential privacy. And the differential because you take the differences of whether people is there or not. And if you replicate it for all the entries in all the records in the database, you have what is called differential privacy. And importantly, this is a definition that can be implemented in code that actually can estimate how much noise needs to be put in the dataset in order to achieve these guarantees. This example was about, let me move to synthetic data. Synthetic data are fake data that reproduce some of the statistical properties of the original data. And if I have, previously I've described some queries, and if I do queries and histograms on the data, then I can use these histograms to generate synthetic data with the same probabilities. Now, there are many ways to generate synthetic data. GenAI has expanded a lot of the type of data that can be generated. By synthetic data generated by any method by itself, they do not give any guarantees. We know that very often the machine learning system, they learn about their training examples, and sometimes they output just the training examples. How can we guarantee that this does not happen? And the way to do it is to introduce a differential privacy step when you compute the histograms in order to prevent that any other method to generate synthetic data reveal confidential information. Now, why do I insist so much on differential privacy? There are many vendors of synthetic data that do not use it. In a survey, I've seen about 50%, about half of the vendors use it, offer it, others don't. I like to compare this to the history of cryptography. The history of cryptography is full of examples of tricks that have been used because they looked hard until someone then discovered that they were cracked. They could be broken with a very dire consequence for those who trusted that. Today, nobody would take seriously any method of encryption does not come with a mathematical proof that it's supposed to be hard according to some clear definition of complexity. And that's the modern cryptography started when people realized that you can and you must prove a certain that breaking a code is sufficiently hard according to a clear definition. Differential privacy offers exactly this the same guarantee that we know exactly what we can protect and what we cannot. Accenture has worked, in particularly the Accenture labs, more than 5 years on this topic, produced various assets, and collected many algorithms, combined with other algorithms that exist in the open source. I show here some demos that have been done some years ago. You may have already seen them. And we have added the new algorithm for some key operation, and we plan to put it open source after completing the tests. Accenture has implemented also one of the largest projects worldwide that use DP. The goal was to connect skills with the industries, and that's very important and a difficult question if you don't have the data, how you connect skills to industries. And even if you have the data, they are extremely sensitive. They don't want to that they could be misused. And this is an excellent case for differential privacy. So why isn't everyone already using that? The ecosystem of differential privacy had been introduced originally 15 years ago, but it took a long time to develop a robust, mature ecosystem. Which is now the case. The robust ecosystem became mature only recently. And of course, as before, you need a legal framework and the major contribution of the project I mentioned before was to define a legal framework that is suitable for this kind of analysis. A technical problem is that each time you use the data, either to do queries or to generate synthetic data, you must take into account that you are kind of consuming a so-called privacy budget. You cannot reuse the data, the real data, too much. Otherwise, you come back to the risk of revealing confidential information. And that must be included in the process. It's not a real problem because you typically want to use differential privacy in the development, in the training, because then when you have the system in production, you might use confidential computing for production, or anyway you will consume much less privacy budget. Another challenge is that this as well requires good data quality and detailed metadata and standardization. And this is what I wanted to discuss next. To make this point clear, there are different challenges for different roles. For instance, for data analysis, machine learning training, statistical aggregates and reporting, the statistical properties of the data are very important. And the data must be accessed multiple times. This is typically accessed by small teams, and the format is assumed to be set up upstream. And this is the typical application which you have most of the literature that applies differential privacy. Another challenge is the data ingestion, the data mapping, the setting up the pipeline, data quality. This is much less requirements in terms of statistical properties. We don't often, correlation are not important at all. We have much less frequent access to the data. But these are typically done by much larger teams. So this is more important because it actually implies higher risk. And here what is important is to ensure syntactic correctness of the data. Now, the wish to perform data checks, data quality, without giving access to the data is the old goal of full automated data quality, which you can do something. You can do some nice checks, but it's not realistic to have really good coverage, because many things can go wrong. And in order to do data checks, you have to make some assumptions. And if you are very conservative, you make no assumptions, you have potentially to do an exponentially growing amount of checks, and it just does not work. In terms of privacy protection, this implies adding too much noise to the data. So and also here, Gen AI and language models are helpful for some specific tasks, but they are not an overall solution, because they make their own assumptions that we are not even aware. So here, what we need are reliable standards. And I connected this to the topic of data streaming, because an underestimated advantage of moving to a data streaming framework is that you abandon all the legacy of importing files, deal with the CSV files that are the cause of a lot of data quality issues. This is the chance to set new standards that enable better control of privacy and better security. So that's another advantage of data streaming on top of what you heard already earlier by Kai. So, a great example of the standardization that we need is what is happening, for instance, in data lineage. Data lineage is the problem of the tool that answers the question, where do my data come from, where are they going, who am I giving access to, who is, what is the impact of my latest deployment. All this is what data lineage tries to cover. Multiple vendors offer their solution for data lineage, but this solution work only for the technology in which they have been built. Cross-platform data lineage is extremely important, but it's a great challenge because these technologies do not talk well with each other. What we need here is a standard, an open standard that becomes a common language between this technology, and this is what the Open Lineage project has been building, and they recently obtained support by major cloud providers like Azure and GCP, data governance tool like Colibra, IBM, Manta, Atlan, DBT, Snowflakes, or data streaming platform like Confluent. Open Lineage defines a structure of the lineage metadata that represent a common language between all these systems. And that's essentially what the kind of standardization that needs to be done also for enabling better privacy protection and better security. I think I am at the end of my time. Briefly, I also want to mention a completely different approach to data privacy that is very different but complementary, because it's the ideal that the people could have more control on their own data. And one promising implementation of this idea is based on the Solid, which is an open standard introduced by Tim Berners-Lee to represent and store the digital identities in a decentralized way. This allows people to decide what they want to share with whom, until when, and it has many advantages for the people who want to have better control on their data, for the business and organization that In this way, you have much better quality of the data. And I want to stress here also to standardize. It will help us a lot because it would standardize the way in which this kind of data are represented. And Accenture is investing in a company, Inrupt, that implemented and commercialized services around this. And that's all.
7 questions for you. If you're ready for them, I can read them.
Yeah.
So why to encrypt already encrypted data with the multi-party room? Also, how can we work with such encrypted data?
The data are encrypted in the disk, but then they are decrypted in the memory. And that's where we wanted to protect it. If in a normal computer, if you do a dump of the memory, then you will read the data clear.
Okay, next question. Is the customer concerned about data being misused or stolen rightful comparing to not having cloud solutions? Sorry, yeah.
I don't understand. I think I need a clarification. Can we need to the...
Oh, maybe someone who had a question can clarify? No? Okay. Okay. So I go to the next one. Would even companies allow AI models to access decrypted PII data in order to generate synthetic data?
No, but what you mean by PII? Because usually we consider PII as a direct identifier, that's just the names and emails, and this is of course something that you don't need to analyze, and it's safe to drop. But many other attributes are de facto indirect way of identification, and this needs to be analyzed in many processes.
Okay.
And,
thank you. Could by synthetic data used as open data, public data interconnected by defined ontologies?
Depends how they have been created, but one nice thing of synthetic data that once they are produced, you can this is the post-processing guarantee of differential privacy, that you can do whatever you want on top of this synthetic data. You will not cause more, you will not reveal. It's impossible to extract more information from those synthetic data. This is called the post-processing guarantee. Of course, yeah. That's,
okay, so
data streaming is also.
Data streaming is also consuming the same data as standard batch processing. So how can it improve data quality, please?
Because it's simply a newer, new technology that does not have all the legacy of dealing with the CSV files and all the perversion of this rather failed standard. Just because it's new and it's the experience of defining metadata and all these things and formats much more modern and robust way.
Okay. Despite encryption, can data be exposed during its transfer to or from the enclave?
In the transfer, the data are encrypted. So that's the standard part of encryption in transfer. I hope there was something. Okay. So encryption can data be exposed? Okay.
Aren't you concerned that the AI could use computing power in ways we aren't familiar with and lead to crypto anarchy?
Maybe. I still sleep at night, but I cannot exclude it. But I'm not the best one to answer.
Okay. Any more questions? No.